You're live now. Hello, everyone. Today we are live from Enlit. You can hear us, right? Yeah. So, hi, everyone. We are today live from Enlit. We'll be presenting the HEART project and the toolkit. With me, I have Claudio from Polyme, Pietro from Europe, and Chiara also from Europe. Claudio will be introducing the HEART project and the toolkit and its cloud-based decision-making system and the energy management system. Pietro will be presenting the energy data from demo cases in Italy and France. And Chiara will be presenting the simulation of it. The HEART project, just to introduce, is Horizon 2020 funded project that is developing a retrofit architectural toolkit that can help renovate old buildings, make it smarter and energy efficient. Without any delay, I would pass it on to Claudio to share his presentation.
Thanks a lot for your introduction. I share my screen. Please tell me if you see it properly. Can you see my screen now?
Yes.
Okay. Thank you. So just let's say a presentation to introduce the project and the strategy for the energy management. So let's say that the building sector energy demand is more or less 40% of the total energy demand in Europe. So there is a strong need to decrease the building sector energy consumption. Moreover, considering the goals set for 2050 that are aiming at reducing between 80 to 95% the greenhouse gases compared to the 1990 levels. In this context, we have to know that just 10% of existing buildings in Europe are energy efficient. So you see here the distribution of the age of the buildings along Europe. So more or less they are mainly old buildings with poor energy performances. Also, we have to know that the average rate of renovation in Europe is between 0.5 and 1.5% per year. So it means that in 2050, just 40% of the current building stock will be retrofitted. So we need to increase this number if we want to strongly and quickly improve the energy efficiency of the building sector. In such a context, we decided 4 years ago to start the HEART project. It's a project founded by Horizon 2020 program. It will end in the middle of the next year. Here you can see the website, the LinkedIn and Twitter account of the project. We, Polytechnic Milan, are the coordinator of this project. We are 16 partners, and let's say the interesting things to notice is that just 4 partners are academic partners. All the other members are small, medium enterprises. So there is a strong contribution of SME in developing technologies and components. The application context of the project is the Central and Southern Europe, where we have a climate that requires heating, but also cooling. So we have to face both problems during the year. And the application target are multi-stories or residential buildings. So the typical social housing building we have along Europe, they are composed by 4, 5, 6 floors. And typically they are linear condominium buildings. And we have in the project 5 objectives. The first one is to develop a systemic cost-optimal solutions for the energy retrofit. So in particular, we want to decrease the installation time, and we want to ensure a payback period lower than 15 years. That is quite ambitious without the subsidies, obviously. The second objective is to develop, update and adapt innovative technologies for their systemic integration. So the idea is to take existing technologies, to update them, upgrade them, and to make them synergistic. So in the way that we can apply the toolkit with a set of technologies that properly interact and communicate between each other. Number 3, we want to foster the building's smart upgrade. So we are speaking every day about smart building, but the issue is how to transform existing buildings into smart buildings, because the new buildings are hopefully already smart, but the existing buildings that are the big problem must be converted into smart buildings easily. The objective number 4 is to support and improve the decision-making process of the retrofit activity. So the idea is to support the designer, the decision maker, to identify the cost-optimal solution to retrofit an existing building. And objective number 5 is to promote energy-efficient financing. So the idea is to foster and to simplify the investment into retrofitting existing residential buildings that nowadays are not an attractive market for investment funds. Here you can see the structure of the toolkit. We have basically 9 components. The first one are retrofit elements and techniques for existing windows. Then we have a multifunctional external thermal insulation. Number 3, we have universal photovoltaic tiles to generate renewable electricity. Then we have a cloud platform. Then we have DC smart fan coils. I will explain how they work later. A thermal storage, a battery pack that is not directly let's say, a product of the research, but is just integrated, is a component, market component, simply integrated in the toolkit. A DC heat pump and a multi-input, multi-output converter. Now I go more in detail. The DC smart fan coils are elements that are intended to substitute existing radiators. So the typical element we have in such kind of residential buildings to provide heating. The idea is to take off the existing radiator to install this new component that can provide heating and cooling. At the same time, using the existing pipes, so the existing hydronic networks of the building, also if the pipes are not insulated. So without invasive intervention on the hydraulic network. Then we have the PV tiles, because if we want to reduce the demand of an existing building, for sure we need renewable energy. And the most convenient way is to use photovoltaic and solar energy. So these tiles are intended to substitute existing tiles in a building. And they can be easily integrated in an existing roof, and they are cost effective because the basic component of the tiles is made with recycled plastic, and then we have a customized PV panel. You can see it in the picture on the right. Then we have a DC heat pump. Again, we are powering both the fan coil and the heat pump in direct current, so avoiding the transformation between DC and AC, because DC current is directly generated by the PV plant, and so is directly used to power the appliances. The heat pump also has a combined thermal storage with PCM, with the aim to store as much as possible the electricity generated during the day when we have the photovoltaic electricity, and to avoid using the heat pump and the smart fan coil during the night, so avoiding buying electricity from the grid. Then the MIMO converter is simply a power converter that is managing the DC and AC fluxes, and it's also interfacing the entire system with the grid, because obviously in some moment we need electricity from the grid, or we need to sell in excess electricity to the grid. Then we have a modular facade with thermal insulation. This facade can be applied, overlapped to the existing walls, and is providing thermal insulation, but also we have an air gap that can be used to install new elements, for example, new wires to power the smart fan coils, or new pipes if they are needed. Then we have retrofit component and techniques for existing windows. So the idea is to maintain the part of the windows that is still efficient. For example, the frame. In this case, you can see in the picture is the wooden frame of the first case study in Italy. It is still efficient, also under the energy point of view. What we did is to substitute the old glass with a new high performance glazing with a good thermal insulation and also solar control features. And here you can see the structure of the cloud-based platform. So we have this cloud-based platform that is working as a DSS, a decision support system, in the pre-retrofit activity. So on the platform, a simplified energy model of the building is running. And through this model, we can forecast the performance, the energy performance, but also the economic performance of the retrofit intervention. And we can provide useful data to the construction stakeholder, to the funding stakeholder, and also to the management stakeholder. So this platform is acting as a decision support system. After the retrofit, the same platform is running the detailed energy model of the building, and is acting as an energy management tool. So the same building model is used to interact with the external services, for example, the information coming from the grid or the weather forecast service, and is providing the energy management logic. For sure, also users can interact with the platform to, let's say, see the performances of their dwelling, for example, or to just change the set point temperature in the specific room. So they basically have a user interface via a mobile app to interact with the system. So you can see here the scheme of the functioning of the decision-making phase. So the platform is simulating the energy and economic performance of different alternatives, different intervention alternatives. I mean, different thicknesses of the insulation, different amount of photovoltaic tiles, different number of thermal storages, and so on, is providing the results in terms of global cost and overall energy performance. So the decision maker can identify the cost optimal option among all the feasible possibilities. Then in the operational phase, the platform is comparing the real energy consumption of the building with expected consumption simulated by the energy model. And if there is a significant difference between the two trends, is providing alerts, let's say, to the energy management, to the facility manager, and to the other stakeholders, also to underline that there are problems under the energy technical and economic point of view. So this way, the stakeholders can immediately interact with the system and identify the problem, avoiding, let's say, uncertainties in the real performance. And here you can see the ICT infrastructure. So all the energy management system is based on robust ICT infrastructure that is using wireless communication. We are using two different standards, Wi-Fi standard and narrowband IoT standard. So the idea is to avoid, let's say, complex and expensive wiring of the building, because we are speaking about existing residential buildings, so we don't want to be too invasive in the dwellings. And this infrastructure allows the exchange of data between all the elements, so the smartphone coil, the heat pump, and so on. A building gateway, that is the brain, local brain within the building, and the cloud platform, that is the cloud brain. So there we have two levels of control. One local level that is within the building gateway, and a cloud level that is always operative and is interacting with the things, the elements on the field. So every component of the system of the hard toolkit is communicating with the gateway and communicating with the platform. This structure allows, let's say, perfect monitoring and management of the entire system. We are applying this toolkit in 2 different case studies. The first one is close to Reggio Emilia in Italy. The work is almost finished, and the second one is Lyon in France. We had some delays in both case studies due to the COVID pandemic, but in any case, we plan to finish the works within the beginning of the next year. And then we have, let's say, around 6 months of monitoring activity to, let's say, to take under control the real performances of the system. Thanks a lot for your attention.
Thank you, Claudio. Thank you, Claudio. I'll just pass on the screen to Pietro.
Hello everyone. So let's start the presentation. Okay, so I want to introduce you to the monitor data that we are collecting. We start the analysis as well of this data, and to see the main impact of the refurbished work that have been performed in the two demo cases. So as already mentioned by Claudio, we have 2 demo cases in France and in Italy. So this is the plant of the buildings, and so we have monitored data from September 2019 up to April of this year. We are monitoring the main indoor conditions, so temperature, relative humidity, and CO2 concentration. And for the French case, we are also monitoring the global electricity and the lighting consumption. And so the main activity was to analyze the comfort condition, and then we also present the main consumption in electricity and in lighting for the French case. So in Lyon, these are the average temperature indoor temperature of the flats that are monitored. We can see that 50% of the time during the winter season, the temperature range from 15 up to 24 degrees. So it's in this range. But if we look at the flat level, we can see that there is an important difference between the different flats. So we have flats that have an average value about 25, 23, 24 degrees, and there are some other apartments that are very low temperature, that is around 15. Here again, I'm showing the relative humidity. Again, are the conditions that were monitored during this time. And again, the values for the cooling period and heating period. Again, for the relative humidity, they are more or less in the same area, but we have some apartment with lower value. This is the CO2 concentration. We can see a trend in decreasing the CO2 concentration. So in the winter 2019 and 2020, the average concentration was quite high inside the monitored flats, and it decreased quite a lot during in 2020. And again, here we see this concentration for all the apartments. Again, there are some apartments with very high concentration and other with lower. We also analyzed the comfort conditions. So here you can see the predictive mean vote. Basically, is a vote is a estimate of the vote that people will give to under certain condition. So the people have 7 possibilities from hot to cold, basically. And so when we are around 0, it means that is good. And then we also compute the predictive percentage of the dissatisfied. So it's basically a percentage of people that will be not satisfied under that condition. And you can see that the mean value is slightly above 5%, 7%. So it's not high actually. But if we look at the single flats, again, here we have the predictive mean vote and the predicted percentage of the satisfied. We can see that we have some time slot during the monitored period where we have some where the comfort was not always optimal. These are for the summertime, and this is for the winter, where we can see where it's dark. Basically, it means that we are far from the comfort, or dark. Here it depends by the K performance indicator that we are looking for. And so as it was shown by the average temperature inside the building, we see that there is some very low temperature sometimes. And the other information that are available in Lyon are the electricity, the global electricity. So here we are seeing the weekly consumption, global electricity consumption of the flats. Here are the total consumption divided by flats as well, and the light consumption, again the weekly one. We are still checking the unit, the numbers. So these are always preliminary data. So let's say it's more a work in progress, but still, yeah. This is what we have. Again, this is the total consumption per flat. And then we have the Italian demo case. So again, social housing in Italy. The data that we collect are more or less the same, but in the Italian demo case, we have also the chance, since they finalized the substitution of the windows in September 2019, we were able to compare before and after that specific intervention. The data that are available from the monitoring system that we received so far were from September 2018 up to April this year. And yes, and the graph and the idea are similar to what has been already shown for Lyon. So these are the indoor temperature of the different apartments available in Bagnolo. Again, we can see the range of the temperature that are different on the apartment, but range from 20 in the winter time, from 70 up to 23, 25 sometime. But in Bagnolo, we are able to see also the difference, before and after the windows refurbished. And we can see that we have a much more compact distribution of internal temperature inside the flats. That means that the temperature inside the flat remain much more constant than before the refurbished. And these are the relative humidity. And again, if we look at the pre-intervention and the post-intervention, again, the distribution of the relative humidity is much more compact now. around an average value that is close to the comfort. Again, these are the main indicators, so the predicted mean vote and the predicted percentage of dissatisfied before and after the intervention. So when you see the graph that is lighter, less intense, it means that we are closer to the comforts. When you see darker spot, it means that we are somehow far from the comfort. Yes, these are the main output that we have a chance so far to analyze. And these are the energy consumption for the air conditioning in Bagnolo for each flat. They are aggregated, so it's the cumulative energy consumption of the air conditioning at weekly with a weekly resolution, and this is the energy consumption for the boiler, always at a weekly resolution. So to conclude, these are the preliminary results. We are still in the process to collect and verify the data that we are receiving. But from this preliminary result, we can see an effect, at least on the distribution of the temperature and the relative humidity as well, that we, just considering only the refurbish of the windows, that already increase the comfort in the flats. So yes, that's all from my side. So if you have any question later, I will answer.
I will then ask Chiara to share a screen and. Yeah.
Can you see my screen? Can you hear me? Okay, so thank you, Pietro and Claudio, for the introduction and the showing of the monitoring data. I'm going to present you the dynamic model of the building and heating and cooling system for the Bagnolo demo case, so for the Italian demo case. Why do we have done the dynamic model is to investigate before implementing the toolkit into the demo case, how the components interact between them and how could we optimize the control in order to implement it as a smart control logic inside the toolkit. So the agenda is we'll present you the building thermal model, how has been done, the calibration of the model and some results. And then secondly, I will show you the dynamic system model and some result from it and investigation of the optimal solution and smart control logic. Okay, so the thermal model of the building have been implemented by Polyme with the SketchUp and Energy Plus model software. And yeah, the aim of this building model is to understand the heating and cooling demand of the building before and after retrofit. In order then to implement the building model into the energy system model, dynamic model. So what have been done is that the building model has been calibrated with the monitoring data. As Pietro already mentioned, we had before retrofit monitoring data and also after Windows renovation monitoring data. We still miss the monitoring data after the renovation of the whole building. So by changing some boundary condition, the building model have been calibrated in order to match the energy consumption resulting from simulation to the monitoring data. Some results from these both monitoring data and after retrofit. We can see that before retrofit, we have a high heat demand, and then thanks to the implementation of Windows renovation and then both Windows and external walls renovation, the heat demand goes down. In particular, we have a lower lower transmittance losses thanks to a better U value of both external walls and windows. And we have also up to the heat demand is lower down up to 80%. If we compare before retrofit and after retrofit results. Of course, these are only simulated results. Then we implemented the building model into the transit model. So we as EURAC have developed the HVAC system model. And the goal of this is to understand the electricity demand, the primary energy demand, to investigate also the control logic, the optimal control logic, to investigate how this system is behaving, how the components are interacting between them. So first of all, we had to build this model with components. So we have built a special component for the centralized heat pump. And then we connected it to the component of the type for studying, for analyzing the storage tank. In particular, we have to thanks to University of Graz for letting us use these components in transits, and also University of Ljubljana for having tested this PCM storage tank. We can see in this slide the behavior of this component. So at low temperature, below 20 degrees more or less, we have inside the PCM the material that is completely solid, and then if we heat up the storage tank, then the material inside melted and it becomes liquid at 30 degrees. So we have a path dependence here. So back again to the system. We have also model a low temperature distribution circuit. We have a water in here that is circulating at around 25 degrees. Since the emission system are not radiators, but fan coils that are micro heat pumps. In particular, they are water-air heat pump, and smart domestic hot water boilers are water-water heat pump connected to storage tank. We have modeled them, one per each dwelling. And yeah, I will not go into detail of the model. Yeah, I will skip this, but if there are any questions, I will answer. But again, the goal is to understand how this system is working, how the components interact between them. So firstly, we had to implement a deterministic, a strong rule-based control logic. That was our baseline, and then from that we analyzed advanced control strategies to find the optimal solution. So for what concerned the deterministic control logic, we have fixed set points and fixed hysteresis. And yeah, I'm not going into the detail of the controls, but yeah, this control logic aims to control the on-off of the heat pumps, of the smartphone coils, of the operation of the mixing valve. And this is our baseline. These are the results of our baseline. So from the thermal model of the building, we have a building energy demand that we already saw. And then from the analysis with transits, we have the total electricity consumption. And we can see that is shared mainly between smartphone coils and heat pumps. I mean, these two components are mainly the main electricity consumption of the total electricity consumption. This electricity is for our baseline is not from PV production, but is only from the grid. We know that with monitoring data, we will for sure improve, and these are only simulation results. So we know that these results will for sure be changed a little bit. And with the advanced control logic, we can have for sure an optimization of this system, and we could reduce this electricity. We could spread the PV production, and I will show you something. For example, if we study the population of the system and the building demand, in some days, for example, in summer days, we can have domestic hot water production, so heat demand during the first hour of the day, and then we can have cooling demand from the building after lunch. And if we if we charge in the correct way the storage tank, we can use the heat of the storage tank to heat the building. So the PCM storage tank releases heat to the building, and then the PCM cool down. And during these afternoon hours, the heat from the building goes to the PCM, and the PCM will heat up, and we do not have to turn on to run our heat pumps. So it's a sort of balance. So if we can study that in a good way the operation of the system, the building demand, we can for sure reduce energy consumption. So if we implement advanced control we can, for example, decide when to charge or discharge the PCM, depending on the PV production, on external weather. If we have, for example, in this graph, it's quite complicated, but if we have a certain temperature difference between like the minimum and the maximum temperature in one day, we can say that if it's worthy or not to charge and use the PCM. Also, if we have dynamic set points, if we set ideal set points for each hour, for the distribution loop, for the set point at which the heat pumps should operate, we can maximize the efficiency of HVAC system. Moreover, if we also study, as before said, if we can predict also this building demand and the weather condition, we could for sure improve our control. So Mariam Mir, a PhD student, has also studied in her PhD thesis some adaptive predictive control, and she has implemented it into the transist model we have built. And she found out that this advanced control can increase renewable energy self-consumption. We can reduce peak load. We can exploit PV production. We optimally scheduling the domestic hot water boilers production, the PCM charging or discharging. Also, we can have a much better control, and we can optimally we can reduce electricity consumption. Here are some results in conclusion. So yeah. I also taken this slide from Mariam Mir thesis. So we can see that if we study the system without PV production, without using of PCM, we have a certain amount of electricity taken from the grid, but if we implement PV and then PCM and then deterministic rule-based control, and then again up to the adaptive predictive control, we can save up to 57% of energy taken from the grid. So of course we have also cost savings. So in order to recap everything I was talking about this, because we in HART Toolkit we will implement this control logic in order to achieve to reach and nearly zero energy buildings goal. So it was a bit technical. I hope it was good to listen, and if you have any questions, just ask me. And now I don't know how to end my sharing. Okay, here.
So we don't have any questions in the session. So I would just I'd like to thank everyone for joining us and all the panelists for speaking. And you can get in touch and get to know about the HART project through our website, which is heartproject.eu. And if you have any further question, you can get in touch through email or through our website. Thank you for joining us today.
Thank you. Bye.